Okay, welcome back, everyone. This is day 2 of our kind of boot camp workshop on astrophysics basics. The talk that we had yesterday should be posted up on YouTube probably by the end of today. It takes some time to process a 2-hour video, and then we'll post up these as well on the website. So if you want to go back and review anything, if we said something too fast, we can you have a chance to kind of look at it again. And again, these slides are already up there, so you'll be able to see those. Today, we're going to have 2 workshops, one on specifically brown dwarfs. So we spent, again, about 2 hours yesterday to talk about the basics of stars and how we measure them and how we get to physical properties. And we missed a bunch of stuff at the end, but you can take a look at the slides for those. Today, we're going to focus more specifically on a specific class of stars called brown dwarfs, which we study pretty heavily. They have their own sort of special properties. The review reading that you were assigned for this week included sort of discussion on brown dwarfs. So this is a good session to bring any questions you had from those reviews, or perhaps the questions will be answered, hopefully, we'll see. But that's sort of the purpose of today. How's everyone feeling? Good, yeah, kind of an odd day in the news. So just wanted to make sure we check in on everyone. Okay. All right. Well, we'll dive into astronomy and avoid the world for a little while. Okay. So let's get started then. So today we're going to be talking about. So one of the things we left off from yesterday's discussion was actually just how stars work, right? We talked about their physical properties, the fact that they have a luminosity, and they have different brightnesses at different wavelengths. That gives us our spectral energy distribution. But where does all this light come from, right? And I think most of you probably know the answer, basically. But when we get into the details of that, we find that there are some limits for what can be a star. And that's actually tied to some properties of quantum mechanics that we'll talk about today. And that gives rise to this class of things called brown dwarfs. So we'll kind of define what those are. We'll talk about how they were discovered. We'll summarize some of the properties of brown dwarfs, particularly their spectral properties, because again, much of your work is based on spectra. That'll lead to spectral classes, and hopefully by the end I'll convince you that they're pretty cool to study because you're going to be studying for the next 7 weeks or so. This starts off, I think when we talk about brightnesses and stuff like that, by kind of asking a really basic question like, why do stars glow? Right? We don't glow in the visible. We do glow in the infrared. I didn't get a chance to show our infrared images, though I think I will later on. But why are stars bright? That's a question, y'all. Hydrogen fusion. Hydrogen fusion. So why do we have light from hydrogen fusion? What's going on there?
Hydrogen nuclei fuse together and release energy.
So close. It's actually 4, but that's okay. Factor 2 in astronomy is not so bad. But why do they release energy? Where is that energy coming from?
From some of their mass.
From some of their mass, that's exactly right. Right. So the source is hydrogen fusion, and it ultimately comes from the conversion of mass into energy. And it follows Einstein's equals mc squared. So this is a full reaction, right? So there's a bunch of intermediate steps, but you start off with something like 4 hydrogen atoms. You end up with a helium nucleus down here. You also shoot off a bunch of other things like gamma ray photons and neutrinos and anti-electrons, which very promptly collide with another electron and form a couple more photons. So in any case, if you added up all of the mass of those 4 hydrogen atoms, we can measure that in mega electron volts. That's the energy equivalent of mass, mc squared. And you add up all the mass here, which is mostly just the mass of the helium nucleus. There's a difference of about 24 million electron volts. Now that sounds like a big number, millions of electron volts. It's actually a very tiny number, but there's a lot of these reactions happening every second, and the cumulative aspect of that is all the luminosity ultimately that comes from the sun. All the light we get from the surface of the sun originates as energy from this conversion from mass to energy through this reaction. So the details matter because as we'll talk about, some of the reactions that happen here tell us something about what's actually inside the star, and actually tells us ultimately one way of finding brown dwarfs. We'll talk about a little bit later. So this is kind of the base reaction. This is the proton-proton chain. And there's actually a few different avenues in that chain. So I was just showing you this reaction that got you from hydrogen to regular helium-4, called the PP1 chain. There's other reactions that can happen. You can take, for example, the helium-3 nucleus that comes here, combined with the helium-4, and you make this unstable nucleus called beryllium. That can decay, that can collide with either electrons or protons, make other elements, but ultimately all of these reactions end up starting with hydrogen and producing helium at the end. Because the amount of mass that you start with is greater than the amount of mass you end up with, some of that mass has to go somewhere, and it goes into energy. And that's the power of the sun. Right? Some of these other side chains are going to be important, as we'll see in just a moment. All right, so this is happening in the sun. It's not happening here. Why? Like why? You know, we got hydrogen here around Earth, right? It's in our water, stuff like that. Why isn't water spontaneously fusing? Yeah, Lena. So why? Oh, to ionize. So ionize, you mean kick off electrons?
Yeah, well, I guess that.
So certainly when we're talking about this, we're talking about fully ionized atoms. So there are no electrons. You definitely need hot enough to ionize.
There's not enough electron degeneracy pressure?
Well, the sun's interior doesn't actually, and we'll get to electrons. That's a big word you just added, electron degeneracy pressure. We'll talk about that in a little bit. But the sun actually isn't electron degenerate, and yet it's definitely fusing because we definitely get sunlight from it. So one of the clues is all these reactions involve just the nuclei. So your comments about ionization is important because we're not talking about neutral atoms coming together. We're talking about the nuclei of atoms. And what do we know about the nuclei of atoms? Yeah, they're positively charged, right? They're made of protons and neutrons, and that's it. Not electrons. Those are on the outer shells. So what we're doing is colliding things that are positively charged, and we're getting them close enough together for another force to take over called the strong force, and that's what binds these nuclei together. But you have to first overcome the electrostatic repulsion of the nuclei, and that's why we need high temperatures. High temperatures and high pressures as well. And so when we look at the inside of the sun, for example, this is the surface that we're seeing, and it looks very spectacular and explosive, but these are just kind of magnetic flare images. This is not fusion. The fusion happens all the way down here in the core, where you've got densities that are about 150 grams per cubic centimeter, and just to mind that water is about 1 gram per cubic centimeter. The densest element is about 10 or 15, so this is really dense plasma. And it's about 15 or 16 million degrees Kelvin at the core. So really high temperatures, really high densities, really high pressures, right? All of these things are required to have fusion happen, because all the things are required to get those nuclei to get close enough together to start fusion. And I mean close enough, they actually have to get close as in like the size of the nucleus to start fusion. That's really close. Right? So we know fusion has to happen in the sun and other stars, because that's where the light comes from. And the challenge of doing fusion practically here on Earth is because you need basically an entire star's worth of pressure pushing down in that site, and also really, really, really high temperatures. It's hard to do in the lab in order for these reactions to happen. So that's the conditions required. And actually, the minimum temperature turns out to be roughly 3 million degrees Kelvin. This depends on density, pressure, and stuff like that. And it's, you know, it actually solves another problem. Not only does the fusion produce the light that we see from the sun, it's also the thing that's holding the sun up, right? The sun is made of mass, and therefore is gravitationally attracted to every part of the sun. If left to its own devices, the sun would just collapse in on itself, right? Gravitational force always attracts, so it should always pull the sun together. So keeping the sun from not collapsing down is all of the thermal pressure that's generated from this very, very hot core, and thereon outward to keep the star from collapsing. So fusion plays two roles. It provides the energy for sunlight, and it provides the pressure in order to keep the sun in this nice stable configuration. It turns out that even fusion itself is actually a nice negative feedback process. So if you squeeze the sun a little bit, it will get hotter and fuse faster and push outward. If you expand the sun out a little bit out, it will get colder and fusion reactions will slow down and will collapse into gravity. So it's a nice, stable system, which is good for those of us who live on a planet orbiting the sun. We want a nice, stable sun. Yeah, we're not getting surprised by heat waves and cold waves. So fusion is, I would say, the key activity of stars, the key purpose, right? And then in the process, of course, they're converting hydrogen to helium. So they're actually changing the composition of the universe through these fusion processes. So any questions on kind of just core basic fusion stuff? We haven't gone into great detail of the nuclear physics, but I figure we want to make sure we do on a good high level first. Yeah.
Does fusion only happen in the core?
Yeah, so fusion's happening in the core. You know, there's some radius range where it's hot enough for fusion reactions to occur, and it will drop off as we go further away because it gets colder. But yeah, all the fusion's happening there. I should say in more evolved stars, the stars after they've kind of depleted all the hydrogen in their core, will start to fuse hydrogen out in kind of shells moving steadily outward from the center of the star. And that's where we go off the main sequence, which we did not get a chance to talk about yesterday because of time, but this is related to the HR diagram. None of our stars evolve off the main sequence in like 100 billion years. So we don't have to worry about that point, but you will see other studies of stars talking about post-main sequence stars or evolved stars. Those are stars that have stopped fusing in their core because they've literally run out of fuel, but they're still fusing on a shell outside the core. Those are things like red giants and stuff like that. Other questions? Okay, all right. So there's a good question here though, right? So we know that the sun has to be hot to have fusion reactions, right? We need those particles to have enough energy to get close enough together, overcome electrostatic repulsion, and fuse together. We also know that fusion reactions produce energy, so that heats up the interior of the sun. So a good question is what comes first, right? Like you need high temperatures to make nuclear reactions happen, but the nuclear reactions are keeping the center of the sun hot. So what comes first? What do you think? Do nuclear reactions kind of kick in and make things hot, or does it get hot enough for nuclear reactions to kick in? Yeah, 50-50 shot to just guess. Yeah.
It's hot enough first.
It's hot enough first? You agree? Yeah? Okay. So that is definitely the case, because really you definitely need high temperatures to start fusion. They can't just spontaneously happen like we used to believe in cold fusion for a little while. So there's a couple of things that's important to keep in mind is that, I think this is out of order. Yeah. So one of the things that's related to this is that stars actually come in different sizes, and one can ask why they come in different sizes. This is something I would have shown in yesterday if we had some time. The key thing is that stars actually start out much, much bigger, right? When they're forming out of large molecular clouds like this one. This is the Eagle Nebula. The kind of, trying to see if I can see it in here. I think it's maybe like over here. So there's a really famous Hubble picture, I think, of this section of the Eagle Nebula called the Pillars of Creation. This is kind of the entire sort of big cloud. This cloud is about 10 light years across. This is a really big structure. It's only part of the gas cloud that's in the surface region. And this is taken with the Hubble Space Telescope, and it's taken with very specific narrowband filters that are focused on emission lines. And when you do that, what you end up is kind of tracing structure because you're only seeing the parts that are glowing in these emission lines. They're actually kind of, there's another hot star over here that's causing essentially resonant emission to come off the clouds, etc. So these are real structures that are out in space, and the structures that are actually actively forming stars. And so a lot of the glow that you see down in here, you kind of, if you look really closely, you kind of see some little red bumps that are kind of behind here, these little pumps and stuff like that. These are the sites of star formation. These are stellar nurseries. And these stars are starting off in these really huge structures. Right? Again, tens of light years across. Remember, the nearest star to the sun is only 1 light year away. So this represents like a good swath of just the immediate solar neighborhood of stars around. And what happens is gravity, right? Gravity is an attractive force. And so if we take one of those chunks, and let's say it's maybe 1/10 of a light year across, so just a little section of that, in the absence of fusion, and when you have enough mass that you've collected, gravity is basically the only game in town, right? So if gravity is high enough, it will collapse down this little cloud of dust. And of course, as it gets more compact, there's more mass in a little area, so the gravity actually gets stronger. So this is kind of a runaway process. So if you can exceed a certain limit of mass, and it's called the G's mass, we won't get into much detail about that. But once you do that, you can actually collapse the cloud into something that's getting smaller and smaller. And just like if I take my keys and I drop them to the ground, they pick up energy. And then when they hit the ground, they make a sound, right? The stars aren't making a sound when they collapse, but they are converting the infall of energy, the transformation of gravitational potential energy into kinetic energy into heat. About half of that heat goes into heating the inside of the star, and about half of it's just radiated away. And that's actually how we see these things. If they don't radiate, we don't see any young stars for it, because that's how we see them, it's light. Right? But it's that gravitational collapse that's getting the conditions hot enough in the core to start these fusion reactions from happening. We start big, we shrink down to the gravity, and that, of course, releases energy into heating, and that heating is happening at the center of the star. Yeah.
How long will this process take? Like, could you view the whole thing over like a few weeks, or is it?
That's a great question. I think, and Roman, correct me if I'm wrong, it's like tens of thousands of years. It's the kind of collapse time scale. It changes over time because if you get more compact, basically then you're accelerating more, you're like getting stronger gravity. So it's an exponential process. So we actually talk about kind of the time scale collapse. It's not like it starts and it ends in 10,000 years. It just accelerates. And it's much more complicated, by the way, than a sphere that shrinks. Right? This is actually much more kind of, this involves gas and plasma, and they're moving in different directions. So this is a very simplistic picture, but it's very short. And actually, that's an important thing, is that it's so short that we actually don't really have a good chance of catching it, right? When we look out in the universe, we're seeing as it is today. And something that happens over just thousands of years of time scale, we're very unlikely to see it because it's happening relatively quickly compared to the time scale of everything else in the universe. This is also happening behind those dark clouds that I showed earlier. So it's actually really hard to see because it's obscured by those clouds. So most of this, this is kind of a picture of theory about how this happens, but all the evidence indicates that this is the process because it's just gravity. It's very simple force. We understand how that works. And again, once gravity takes over, there's really nothing, at least at the start, to prevent that from just continually collapsing the star down. That's the right time scale, Roman? 10,000 years, roughly?
Maybe we'll just have a million years.
Well, a million years, we've already got our protostar. So this collapse process, I think, is actually faster than that. But at some point, we have
from the cloud to the main sequence, or
I mean, yeah, just the collapse process. So we start to see stars about 1 million years. So it's got to be shorter than that. So it's of order tens or hundreds of thousands. But we don't measure it.
it's a pretty full time thing.
Yeah.
Yeah, that should be very fast.
Yeah. Yeah. So this is the birth of a star, right? And it's not a star yet because it's just hot in the middle. It's not fusing. Remember, stars fuse. But if the center of the star gets hot enough, because it's shrunken enough, that's when fusion reactions can start to kick in. And so if you have a star like the sun with a mass like the sun, it gets to roughly a solar diameter, right? It actually starts fusion a little bit earlier than that. But once that mass kind of shrinks down again from 1/10 of a light year down to the size of the sun, you've now liberated enough energy from the gravitational collapse to get it to 3 million degrees Kelvin, and then the nuclear reaction starts to kick in. And those nuclear reactions then up the temperature even higher, right? So if we start at 3 million Kelvin, we start nuclear reactions, we're going to get even hotter because of that reactions are producing even more energy. And now that thermal pressure is counteracting the gravitational pressure that's there. And this is when we get to something that's like a stable star like the sun. Where the thermal pressure pushing out and the gravitational pressure pushing them equal each other because it's actively fusing. Okay? So we call that situation thermal and hydrostatic equilibrium. Thermal equilibrium because it's staying at a constant temperature, because the energy that's coming out from fusion exactly equals the energy that's being radiated away from the surface. So there's no net gain or loss of energy, so you stay at the same temperature. Very high temperature, but you're staying constant. And we call this hydrostatic equilibrium because the star is neither expanding or shrinking. Those two forces are in balance. Okay, so that's a normal star. We call that a main sequence star. That's what the situation the sun is today. Questions on that? And folks online, if you have questions, you can either raise your hand or put it in the chat window. Yeah, Colin.
You know, when it first forms, it's like a bright blue giant.
No, so when it first formed, so this actually goes, this is a good question because it goes back to what we talked about yesterday. When it first formed, those clouds, one thing I didn't mention, those clouds are really cold. They're about 10 Kelvin when they're just dark clouds. And by the way, you can see these dark clouds in a dark sky night if you look at the Milky Way. The Milky Way is not just a swath of light, there's dark patches. And those are the same molecular clouds that I just showed at telescope. They're really cold when they start off. And then they heat up as they get warmer. But remember, they're still, up to this point, they're going to be colder than the sun. So if something's colder than the sun, do you expect that to be a blue star or a red star? Yes? A red star, yeah. Lower temperature, more light at longer wavelengths. So in fact, before it gets to the stage where it's peaking in fusion, the stars as they collapse are actually what we call kind of red. They're not quite red giants, because giants is kind of another post-main sequence branch, but they are kind of bigger than normal red stars because they're still heating up. When you talk about blue supergiant or something like that, that's actually the end state of evolution for like a really massive star, and that has a whole bunch of other stuff going on to get to that very high temperature. Because blue means high temperature. But as it's heating up, it's got to be a red star first before it becomes a yellow star like the sun. Okay. Questions? Yeah, Lena.
I first thought, or I guess I learned that young galaxies are blue and old galaxies are red, usually because of the high star formation region in the young galaxies.
Yeah.
So I was wondering, are they blue for a different reason other than the stars? Is the stars that they are older, so they're more red?
Well, so keep in mind that this is happening pretty quickly. This is, you know, as Roman said, that we're starting to see like the first star when they're starting to fuse about 1 million years old. So that's just, we're talking about like one star at a time. Now, if we look at a bunch of stars, right, we're gonna have a whole range of masses, and I think we'll talk about that a little bit. And the more massive stars are going to be hotter and brighter and bigger, as it turns out. And so in a young galaxy or an actively star-forming galaxy, you're basically seeing mostly the young, bright, massive stars, which are all blue. And then over time, those die, and then we're left with red giants, cooler stars like the sun, red dwarfs, which don't really see in other galaxies. Right, so that's the reason we call young galaxies blue, is because we're seeing those young hot stars that are massive, and they outshine the young low mass stars, which are much thinner and much better. But when those young massive stars die, and they die quickly, then we get to see the rest of the stars. Yeah. Any other questions? Okay. So this would be something like the sun, right? It shrinks down to about the size of the sun, and it starts to, you know, find its way in this AKA main sequence balance here. Now, if we have less mass, so let's say we have 1/10 of the mass, right? Remember that gravitational potential energy, right, as an equation is Gm squared over R, so it depends on mass. So if I start with less mass, I'm going to have to actually shrink this object down more to get to the same temperature, right? Because the idea is I want to get enough energy out of the collapse to get to 3 million degrees Kelvin or before. And for something like the sun, it does that when it reaches roughly the size of the sun. But something that's smaller has less potential energy to start with. So we're going to have to shrink it down further to get to that temperature. And in fact, the scaling relation is that the mass of the temperature of the core roughly scales with the ratio of the mass to the radius. So big mass star, like high mass star, like maybe Vega, something like that, doesn't have to shrink as much. It can go to a big radius, and turn on fusion. A small mass star is going to have to go to a small radius in order to turn on fusion. Right? And so that's what happens with something that's maybe like a tenth of the mass of the sun. A low mass star, the kind of things that we look at, it has to shrink down even further in order to turn on those nuclear reactions and then have the nuclear reaction thermal pressure balance the gravitational pressure. So that gravitational potential is key. That collapse part of it is key. It sets the size of the stars when they're fusing, and it's dependent on that. So it's linearly dependent on that. We can see this if we go out and actually measure stellar radii. So this is a plot from a paper that came out 7 years ago. And what these authors do is they use a technique called stellar interferometry. So they use a whole network of telescopes, optical telescopes. They look at the same star with all the telescopes at the same time, and they use interferometric techniques. So interferometry is like when you compare light waves and you see if they superimpose and they constructively or destructively interfere. It's a way of actually measuring things in space at extremely high angular precision. So high that you can actually resolve the surfaces of stars, nearby stars. And so what this study does, they looked at a whole sample of stars going from a solar mass, so like the sun, down to roughly a tenth of a solar mass down here. And they physically measured the radii. And you can see this dashed line is if the radius to mass ratio is 1. And you can see it's pretty close to that. Right? There's a little bit of variation because there's other physics going on, but that's a pretty good confirmation of that sort of very simple scaling model. Okay, so mass, the more massive your star is, the larger it ends up because it doesn't have to shrink as much to get those fusion reactions going. Whereas lower mass stars have to shrink down to much smaller sizes in order to get hot enough for fusion reactions to happen. Okay, any questions on that? All right, so here's a question. What happens here? Right, if I have a very, very low mass star, let's say I have a mass of a star that's the mass of an apple. How small would I have to shrink it to get down and let it start fusing? So it's helpful to know some numbers here, right? So the mass of the sun, right, and the radius of the sun, right? So that's a good starting point. Mass of the sun, to make sure I do this in kilograms, I think it's like 10 to the 33 grams. Roman, I'm flipping with you here. I'm a little tired. Mass of the sun, 10 to 30 kilograms, to 10 to 33 kilograms, yeah. So the sun is 10 to the 33 grams. Any guesses on the mass of an apple? A little easier to estimate. Is it 1 gram? Is it a kilogram? Best order of magnitude guess. Sure, 100, I'll go with 100 grams. All right, that's probably not too off, right? Maybe it's 200 grams, maybe it's 50 grams, but 100 grams is a good guess. So the sun is 10 to the 33 grams. An apple is 10 to the 2 grams. So it is 31 orders of magnitude less massive, which means it would have to be 31 orders of magnitude smaller for fusion to happen, if this relation goes all the way down to 0, right? Well, the size of the sun is exactly 1 solar radius, so that doesn't tell you very much. That is about 7 times 10 to the, let's do this in meters, centimeters, 10 to the 10 centimeters, right? So in order to shrink this down to the size that would start fusion, I have to divide that number by 10 to the 31, right? Because mass and radius are proportional. So that's going to be 10 to the minus 21 centimeters. And that is equal to 10 to the, so let's do like an atomic unit, right? So anybody remember roughly the size of an atom, with the nucleus of an atom? The particular useful unit of physics. What is it?
angstroms, 5 angstroms or 15?
So Bohr radius is going to be for the electron orbitals, and angstroms, for those who are not familiar with that quantity, is 10 to the minus 10 meters or 10 to the minus 8 centimeters. But that's the size of like the electrons in the atom. What's the size of the nucleus? Is it about the same, or is it smaller than that? It's got to be smaller because it's inside. All right, has anyone heard of a femtometer? Right, it is. That's 10 to the minus 15 meters, or 10 to the minus 13 centimeters. That's the size of a nucleus, right? Now, I said I had to shrink the apple to 10 to the minus 21 centimeters. And a nucleus is 10 to the minus 15, right, 10 to the minus 13 centimeters. Can we shrink an apple to the point where it can do fusion? No, we have to shrink it many orders of magnitude smaller than a nucleus, and we need nuclei to do fusion, right? So clearly, we cannot shrink this apple and allow it to cause fusion, because we'd have to shrink it well below the point where you need a nucleus. So there's got to be a lower limit, right? There's got to be a point where this line stops, and we can't have stars that collapse and start fusion. It has to be. So it turns out you don't have to go as small as an apple, right? So this is a question: how small can a star be? And you actually run into another problem well before you have to get below the size of the nucleus. This is to what Melina was mentioning earlier about electron degeneracy pressure, quantum degeneracy. This comes from quantum mechanics. This is a quote from Wolfgang Pauli back in 1925, or so 100 years ago from now. No two identical fermions, particles with half integer spin, may occupy the same quantum state simultaneously. Now that's a lot of jargon, so let's kind of unpack that a little bit. Fermions, particles with half integer spin. Again, for the physics majors, what's an example of a fermion? Yeah. Protons, neutrons, electrons, kind of actually most of the particles we usually think about, fundamental particles, right? These are all fermions, and they all obey this rule that they cannot occupy the same state at the same time. Now that's a really important rule for us, because if it didn't exist, everything would just basically collapse down into a very dense clump of nothingness, and we would not have stuff like people and planets, right? We need fermions, this kind of Fermi policy here. It has other kind of weird things. So the good translation is you can't put two things in the same place at the same time. It's not quite right. This is not, you can't put two things in the same place at the same time. If you go to Tokyo during rush hour, the subways are so crowded and they actually have people that are, their job is to kind of get people as packed in as tightly as possible. But there's a limit, right? At some point, you can't put two people in the same place at the same time, so you can only put some people in the train. That's kind of, I would say, subway degeneracy, right? Quantum degeneracy is a little bit more complicated, because when we talk about two things in the same state in the same time, it's not just the same place, but also the same state of physical parameters. So that includes things like their energy, their momentum, and their position. So another way to think about this is, I think degeneracy in terms of parking is probably a more appropriate model, right? So if you think about the parking spaces as states that cars can occupy, if you're in a, very open parking lot, you can just casually find a parking space, no stress, you just all find the parking space and come to a stop and everything's good, go shopping, right? But if you go to a really busy place where there's very few parking spaces available, but lots of cars trying to get them, right? This could be kind of a dangerous situation, right? People get kind of aggressive in those cases. They're rushing to get to those spaces. They're roving around. They can't stop because there's nowhere to park, right? They literally have to keep moving because there's nowhere to come to a rest. So the same thing happens when we talk about a very dense gas that's made of fermions, like electrons, for example, right? If there's lots of open states for electrons, then eventually they'll just find their place in there and things will settle down, right? But if there are very few spaces available, then a lot of these electrons that might be at a higher energy state can't go down to a lower energy state and kind of, slow down its vibrations, because those states just not there. So instead of cooling off, they just keep vibrating crazy because there's nowhere for them to cool off to. The state that they want to cool off to doesn't exist because it's already occupied. Right? So kind of like the aggressive drivers, you end up with some aggressive electrons, or it could be protons, could be other kind of different particles. But these aggressive electrons, which can't cool off, exert a pressure, right? They're jiggling around, they're moving really fast. That's pressure, right? That's kind of a form of thermal pressure. But it's a result of this kind of lack of places to cool off to for these electrons. So when you mention electron degeneracy pressure, that's the pressure. It's these electrons that cannot cool off because there's nowhere for them to cool off. There's no state available for them to do that. Now, this is a really special state of matter. We don't normally see this, although we actually do see it a lot, because if you think about the tables here, right? Why is it that I can't put my hand through the table? Part of them not strong enough for that body, right? But why can't I just like push down on this table and compress it down and like kind of through it? Why is the table solid? Let me ask it this way: why isn't the table liquid or gas? Yeah, there's bonds connecting the atoms together, right? And the molecules together. And so that forms a structure. Those bonds are made of electrons that are in degenerate space. They can only occupy certain orbitals. And they can't, they can be kicked out if you heat up the table, it will start to melt away. But they can't, for example, collapse down any further because they are stuck in a degenerate state, right? That's why the atoms are, 10 to the 5 times bigger than the nuclei. Those electrons can't shrink down their orbitals because they're stuck in this degenerate state. So in fact, degeneracy describes a lot of matter, particularly solid matter. This is different because these are just free electrons, and they are just wandering around in the space, and they just can't cool off. So they act very differently than normal gas, where if I turn down the temperature of this room, the gas would get lower density and lower pressure, and it would fall into low energy state. If I turn down the temperature for this stuff, it doesn't do anything. It stays exactly the same pressure and the same density. So it behaves very differently than the kind of normal ideal gas we talk about. We talk about the air in the room, for example. That's a lot of physics. Any questions on that sort of detail? And I'm doing it very hand wavy, so I'm not giving you the equations because that might completely scare you away from this research. But this is kind of the principle of what's happening for these very dense gases. No questions of mine. Okay, so I'm telling you all this, right, because these kind of states happen when you compress a gas to extremely high densities and pressures. And remember, what we're trying to do is take a star and compress it down to very high densities and temperatures to start those nuclear reactions from happening. So this is something that kicks in for these low mass stars because they are just getting shrunker and shrunker, getting smaller and smaller because gravity is pulling them in. You don't have this pressure going outwards. And so this kind of kicks in for these objects. So back in 1960s, about 50 years ago, 60 years ago, people, theorists were asking this question, and so they did some calculations. And so what this plot is showing is models for the insides of sort of toy stars. This is showing what the core density is, right, at the center, and the core temperature. And the way to think about this is that a star starts down here and it evolves this way, it collapses, so it gets higher density, and the energy from that gravitational collapse increases the temperature, right? So this is what a normal star does before it starts fusion reaction. Right, so it gets denser and denser and hotter and hotter, and this line is showing the point where we've crossed this threshold where this degeneracy pressure starts to become really important. Remember, degeneracy pressure is kind of like a thermal pressure pushing outward. So at some point, if this star gets to the point where degeneracy pressure becomes important, what basically happens is it stops collapsing. Because now there's a new force in town that's preventing the collapse. It's the degeneracy pressure. So before we had to wait for a nuclear reaction that ups the thermal pressure to stop the collapse. Now we've got this other source of pressure that stops the collapse before we get to 3 million Kelvin. And that's what's happening with these models. These models here don't reach a temperature of 3 million Kelvin. And so they get to some maximum temperature, they stop shrinking, and then they start radiating away that energy and they get colder over time. but they never get to the point where they start fusion reactions. So these low mass models or low mass stars are essentially failed stars. They never get hot enough in their cores to start fusion reactions because they have this new source of pressure to keep them from collapsing. And that is a brown dwarf. That's the definition of brown dwarf. Essentially a failed star. It's something that's held up by electron industry pressure. It never gets hot enough to fusion reactions, so it doesn't fuse elements. It doesn't have that source of energy. Okay? And the limit for this turns out to be something like 7% of the mass of the sun. So in fact, not much lower mass than the stars I was showing in the previous plot, but that sets the lower limit for stars. And it's a little bit of fudgy number because it does depend a little bit on the abundances of the object you're looking at. But essentially anything that's more massive than 7% of the mass of the sun is a normal star. Anything that's less massive than that is this new class of object called brown dwarfs. Okay? Question? Okay. All right, so this is kind of what this looks like, right? So a normal star like the sun, right, it's going to be more than 3 million Kelvin degrees at its core. It's supported by thermal pressure from fusion, and then the energy that's radiated away is roughly equal to the energy that it gains from fusion. So it's in balance, both structurally and thermally. Whereas these brown dwarfs, they never get hot enough in their cores to start fusion, so they're less than 1 million degrees Kelvin. They are physically in balance, right? This electron density pressure prevents it from collapsing from gravity. So they're structurally constant, roughly, but they're still radiating energy away, but they're not making up for that energy from fusion. So these things are not in thermal balance. They're going to be cooling over time because they're literally leaking all of their energy out, but they're not making any new energy in their cores. So these are different objects because they change over time. They cool off over time. This is a set of models that show how this cooling happens. So what you're looking at is this term effective temperature means the temperature of the atmosphere, right? What we can see with our telescope. And then this is over time, and this is, by the way, on a log plot on the bottom and linear plot on the side, a little bit next here. So we're going from 10 million years here to 10 billion years at the other end here. Remember that the universe is about 13 or so billion years old. And these are just models with different masses. So the most massive models up here, you'll have this kind of period of cooling down, but then they come into balance, right? The amount of energy that they're losing from radiation is balanced by fusion, and so they stay at a constant temperature. So that's one of the key kind of observables of a star. It stays basically constant over a long period of time. But at some point, we get to these objects that they start cooling, and they just keep going. They just keep getting cooler and cooler over time. Those are brown dwarfs. And the difference here, this is somewhere around, again, it's about 0.075, depends on the model, which number it is. But again, about 7% of the mass of the sun is where you transition from these things. Now, there's another sort of class of objects sometimes people throw around, particularly if they're looking for NASA funding, as you get to even lower masses. So hydrogen is one thing you can fuse in the star. I showed that kind of chain of different proton-proton reactions. There's other things that fuse inside stars that can sometimes provide energy for a short period of time. That's why, for example, there's these kind of changes in slope for these different models here. But below about 1% the mass of the sun, nothing can fuse inside of the star. So there's no extra source of energy. So these things just collapse and, they shrink down. They get to this electron degeneracy stopping point, and they just cool off for their entire lives. Now, the numbers here are important, right? How hot was the sun, as I talked about it yesterday, on the surface? Yeah, 6,000 Kelvin. So notice that these coolest stars are a little bit more than about 2,000 Kelvin, right? So we can quantify like the minimum mass of the star, about 7% mass of the sun. You can also say that the coldest a star can get is something like 2,000 Kelvin. And then below that, these objects, all of these things are brown dwarfs. They're going to cool over time. And then you get to really low temperatures. The bottom of this plot here is about 500 Kelvin. And you've got tons of models that run through that region, right? So if you wait enough time, you can get some really cold brown dwarfs. And you're going to see a couple of examples. All All right, one last thing. Why is this called a brown dwarf? This is, we have lots of weird jargony terms, right? You could say, well, maybe these things are actually brown. They're not. The brown is not really a color we normally see for stars. We use for asteroids. This term was coined by Dr. Jill Tarter. Has anyone ever heard of Jill Tarter before? They know who she is? Any of you heard of the SETI project, Search for Extraterrestrial Intelligence? Or watched the movie Contact? So the main character in that movie is actually based on Jill Tarter. She's the one that really started, she's a group of folks, but she's been very active in study and research since the 1960s. But she first did her thesis project, her PhD thesis project, investigating theoretical models for the atmospheres of this new class of brown dwarfs that we had just conceived of. And she coined this term in her thesis, brown dwarfs, which we all use today. And the reason is that because these objects change over time. We've talked about kind of red stars and blue stars and stuff like that. These things are changing their colors as they evolve. So there's not one color for these objects, because they can change. You're going to get redder and redder in different bands. They may get in different colors and stuff like that. So there's kind of many colors these objects can come in. And so she used this term brown dwarfs to kind of encompass the kind of multicolor aspect, at least at the time when they were modeling what they thought brown dwarfs would be. So brown is not the color of the star, but it's just a term we use to kind of, just historically, we keep using it. But the reason we use it is because these objects actually have a wide range of different properties because they change over time. Okay. All right, any questions on kind of the basics of brown dwarfs? A lot of physics. Bring in the remote folks here. Luke, Juan Diego, any questions?
I'm good. Everything makes sense so far.
Okay, all right. Other questions in the room? Drink of water. Okay. We will push on then. Oh, wait, I see a question in the chat. No questions, Mark. There you go. Okay. All right, so now I want to talk a little bit about what we're doing with these objects and why they're important. So I'm going to ask you first a kind of a polling question. So I mentioned really briefly yesterday the spectral sequence of stars. Remember that is based on what the spectral appearance is. And what I didn't get a chance to really talk to you about was the fact that the O stars are the most massive, the largest, the reason we just talked about today, and also the hottest and brightest of the stars. It goes then O, B, A, F, G, K, M is M dwarfs, which are the smallest stars, the lowest mass, the coolest, and the reddest, and the faintest. So you got this full range, and then our sun is a G-type star, turns out, somewhere in the middle here. Any guesses on which one of these spectral classes comprise the most common type of star in our Milky Way galaxy? Yeah. Why M?
Because the hot stars are young, so there aren't going to be, even though they're larger in mass and more visible, there aren't as many of them. There's a lot of stars that right now cool down to white dwarfs, so there's going to be more white dwarfs, or just dwarf stars in general.
Yeah, so you've actually touched on an interesting kind of concept that we call, so what we're talking about right now is something called the mass function. Mass function is a fancy name for saying what is the number of stars as a function of mass. And what you've actually touched on is there's a difference between the initial mass function, the number of stars formed as a function, actually formed as a function of mass, and the present day mass function. Because you're absolutely right. These stars, which, these only last for maybe a million years, a couple tens of million years, right? They'll die off pretty quickly. So even if we formed a lot of these stars, there's not a lot of them around anymore because they all die off. So that's a good point. Present day, certainly these are very rare. So let me back up a little bit and say, what is the most common ones that get formed in the first place? Are we more likely to form the most massive, the least massive, or somewhere in the middle? What do you think? Least massive, so same answer as Dwarf. You guys you did your reading ahead of time, didn't you? Yeah. Okay, good. All right. Yeah, and that's the answer, right? And it's not even close, right? 70% of the stars in the Milky Way, at least in the solar neighborhood, are these tiny little stars, right? They overwhelmingly are the most common types of stars that we have out there. This is actually known a long time ago. This is a plot from back in the 1950s. Edwin Salpeter is a very famous astronomer. I think he's now passed away. But he's the first to kind of really start to measure this quantity we call the mass function. How many stars are there as a function of mass? This is from his 1955 paper where he first measured this. I've never figured out what these little circles are, but this is kind of the overall trend that he inferred by counting the stars in the region of nearby near the sun. And keep in mind, this is on a log scale, right? So, if you look at massive stars, this is in log units, so this is 10 solar masses, right? These are actually O stars, not these stars, right? We go to things like the slightly bigger than the sun, for example. Here's the sun right here, right? That might be 10 to the 8, and then 10 stars, 10 to the 9, but that was kind of a lower limit at the time because it's actually very hard to see these things because they're so faint. So back in the 50s, we actually didn't know a lot of the M dwarfs around the sun because it was really faint for optical telescopes. So even back in the 1950s and 60s, people said, well, what if this line kept going, right? Because we can't really measure these really cool things very well. What if we were to extend that line out as far as mass of Jupiter or something like that? How many stars would we find in it? Well, it turned out that was an interesting question because there was another problem that we had, is that there was a whole bunch of dark matter. I think these slides are out of order. Oh, okay, I guess they don't. So I don't have the slide up here, but there's another sort of big question that's still in astronomy, and that's the question of what is dark matter? Have you guys heard of this term dark matter before? So we can infer the existence of this stuff based on the way that stars orbit around galaxies, based on the way that background light is lensed by clusters of galaxies, right? We have all these kind of different ways of kind of measuring the presence of dark matter, but we still don't know what it is. And right through the 1990s, one of the candidates for this was brown dwarfs. Because again, if you extended this line out, remember this is a logarithmic line. So every kind of step of 1 here is a step of 10 in density. You can imagine you could have a lot of these little things, and they might add up to be literally dark because we can't see them, matter because they're made of mass. Right? And like I said, this is a paper that came out in 1990. And the reason is people were saying that right now the limits at which we can set for brown dwarf detection is still consistent with those objects, which at this point no one had actually found yet, could be dark. So there's a lot of excitement. So remember, the theory for brown dwarfs started in the 1960s. And there's a lot of interest then to start finding these things because, if you can find them, you could get a Nobel Prize, right? So like if we look at like the Nobel Prizes, right, almost all of them come from normal matter, right? Think of like every measurement of every weird thing in physics is all normal matter, right? There was a Nobel Prize offered in 2011 for the discovery of dark energy based on the inflation of the universe. But no one has gotten a Nobel Prize for dark matter yet, right? That's where you want to get your goal, right there, right? So for decades, people were thinking, if brown dwarfs are dark matter, and I find enough of these brown dwarfs, I have solved one of the biggest mysteries of the universe, right? What is this missing matter? So in the 1960s, when the theory came out, no one had found any brown dwarfs at that point. 1970s, no one found any brown dwarfs. 1980s, when I was a kid, I remember watching a morning show and someone was on there talking about the discovery of a black dwarf that could be this missing dark matter and how exciting it was. This is an object called VB8b, and it turned out to be an artifact. So what happened here? It turned out to be an artifact, didn't exist. So that's a bummer, right? So 30 years of detection, no one had found anything. So even as late as 1994, which is actually when I was an undergrad here at UCSD, people were starting to think, well, we've been looking for these for like a generation, and we haven't seen any brown dwarfs, there's a good chance they just don't exist, right? Maybe this theoretical object is just theory, right? It's not something that actually can form. Maybe there are reasons that you don't form brown dwarfs. Maybe you just keep piling on mass to make a star, right? All sorts of arguments for why you can't make brown dwarfs. But the reality is we probably just couldn't see them because at the time of the 1990s, we also had another revolution coming in, and that's the use of infrared detector technology to study the skies at wavelengths that are beyond what our eyes can see. Most of astronomy through the 1980s is all based on optical light. In fact, it's still to some case that's still true. A lot of when we talk about like the Sloan survey or spectroscopy, most people are referring to optical measurements. But there's more to the electromagnetic spectrum out there. And thanks in part to the military developing these technologies, the astronomers started being able to make use of these detectors to see the universe at different wavelengths of light. And that happened in the 1990s. So remember that these little stars that are the most common are also very red and cool. And again, they're cool because they are low mass stars, and they're red because low temperature things emit light at longer wavelengths. Let's get this. All right, so again, this is just that same slide from the other day, right? Cool things like an dwarf, which are here, are emitting most of their light actually outside the electromagnetic spectrum of that our eyes can see, beyond the red, the infrared. So if we want to go to lower temperatures, we have to go even further into the infrared. So this is what one of these detectors look like. This is actually something called the Raytheon Y4K. This fits in the palm of my hand, obviously. I actually held one of these things. This is more expensive than my house, this little device. There's a lot of technology that goes into making these detectors, not like normal cameras or normal CCDs, because they're detecting very low energy light. So you have to actually essentially grow the crystal that makes up these detectors. So this one is made out of, I think, mercury, cadmium, and telluride. Other ones are made of indium and anyway, they're made of like, very rare earth elements, because those elements have to be chosen in such a way that they can essentially detect this low energy light and release the photons to the photoelectric spectrum. So these are special devices, very expensive. They go into these big instruments because you also have to keep these devices very cold. Because remember, we're all emitting infrared radiation right now. If you're looking for faint objects in the sky, you don't want to be completely blinded by just the instrument itself glowing all around you. So these big devices are here because you're keeping all of the instruments cold, and depending on the instrument, it could be down to kind of liquid nitrogen, about 77 K, or in some cases down even to helium temperatures, liquid helium temperatures, 4 K, going way out in the infrared. So this is a lot of technology just to look at the sky in the infrared. But if you do that, it's actually really great, right? So if here's like an interesting picture of Orion, right, in the visible. The lines kind of give it away, but if you didn't see the lines, it'd be pretty obvious that here's the 3 stars in the belt. You've got all of the stars right out there. More Orion kind of comes off with the arms in that direction. That's what Orion area looks like in the visible band. This is what it looks like in the infrared. There's all kinds of new structures that we see around the Orion region. And part of that is because I think the ONC is down here, right? In the scabbard, yeah. So most of this region is these dark clouds that are making stars. And in fact, one of the nearest stellar nurseries is down here in the belt of Orion. And if you have a good set of binoculars, you can actually see this pretty well. This is where kind of million-year-old stars are actively forming right now. And they're forming in this kind of embedded, glowing, dusty molecular cloud, right, which we can see in the infrared. Can't see it here in optical. When you start to look at different wavelengths of light, you actually see different things in the universe. In this case, we're seeing these major massive structures that actually make stars. You can see like a little bubble that's formed around this star. You know what that bubble is from? I think that's no, this is L delta. I'm not sure which one this is, but we sometimes see these bubbles in these gas clouds because the stars themselves have emitted a sort of strong wind, or they've gone into outbursts and they've actually cleared a cavity in this kind of cloud. There's likely a massive young star that's kind of, throwing stuff off as it's dying. But you have no indication of that in that picture, but you can see this very clear structure. So lots to learn when you look at different wavelengths. This is another picture of a galaxy. We were talking about like star-forming galaxies earlier. This is a beautiful galaxy, Mystery 81, in visible light. So you kind of see all the sort of spiral patterns here. But when you look in the infrared, you really see the spiral patterns because you're looking at a lot of these star frame regions, which are again, are these cold clouds of dust where the stars are forming. And you can see them really clearly in this infrared band. You also see there's a big difference between what's happening in the middle and what's happening outside. You learn a lot more about the populations of galaxies. You can do this with people, right? So I mentioned that people glow in the infrared because we have a temperature on our surface. So these are infrared pictures of people at like a talk I gave a few years ago. Just happen to have an infrared camera, so take a picture of people and show them what they are. What are some weird things that you're kind of seeing in this picture? The things that might surprise you.
Glasses?
Yeah. What's happening with glasses?
Like they could be copying.
Yeah. So they're not wearing sunglasses, they're wearing eyeglasses, right? So these are transparent in the visible, but totally opaque in the infrared. So that's another thing, that materials will have different properties depending on what wavelength you like to look at. So yeah, they didn't come to my talk and all had sunglasses because they were cool. These are just eyeglasses. The eyeglasses block infrared light, the glass blocks infrared light, but passes visible light. It's also, important to note, like our skins are where most of our radiation is coming out. Right? Our clothes are protecting us a little bit. Here's a couple pictures of animals in the infrared, right? So, baby fur does not, allow heat to come out very well. It's all coming out through the eyes and the regions where you have gas in the fur. Dogs cool off through their ears, and you can see that in the infrared, right? That's where all the heat's coming out. What else is cool? There's another dog that's getting its heat out through its mouth and its eyes. That's why dogs pant. So a lot of that is just heat radiation coming out because it's not coming out through the fur. So, you learn a lot about how our bodies work in the infrared because, again, we're seeing something different about how radiation is interacting with our skin and with our hair and with our fur and stuff like that. So it's a cool world out in the infrared. We learn a lot by looking at these different wavelengths. So we've taken these kind of detectors and we've put them on surveys of the sky. This is actually done pretty early back in the 1980s with a satellite mission that did this. When I was a grad student, I used this particular survey called the 2 micron offset survey. This is 2 telescopes, one in the north, one in the south, that image the entire sky in the near infrared. Here's another satellite that's still in operation called the Wide Field Infrared Survey Explorer that's looking at it at longer wavelengths. And then there's actually a long list of surveys to this day that have used infrared, and that's probably not even a complete list. They've used these infrared detectors to map the sky at wavelengths that are beyond what we can see with our eyes. Right? So again, it gives us a better picture. For us, this is great. For those of us who study cool stars, it's very important because it allows us then to study and detect these stars that only glow in the infrared. So to kind of illustrate this, this is a picture of one of the brown dwarfs that we study from time to time. Excuse me. This is a visible light image, and it's inverted, so the stars are dark and the background's white. It's just easier to see that on a screen. So that's a visible light image of our brown dwarf, and here is an infrared light image of our brown dwarf. Where is the brown dwarf? So I'll go back to visual. And then I'll go back to infrared. Folks see it? I'll go back to invisible again. And then to infrared. And Roman said blink it.
Yeah,
So yeah, I know. I'm building to that. You guys see it yet? Okay, if you haven't seen it yet, sometimes the universe puts a big circle around it. There it is right there. So there's the infrared, and there it is in the visible. And I know that there's a little smudge underneath it, but that's actually a background thing. So this is a star that's literally invisible, right? It is not detected in the visible bands where earlier surveys were done, but in the infrared, it's obvious. It's actually not that faint, right? It's comparable brightness to some of these other sources in here. And again, this all goes back to that black body distribution, right? When you get to lower temperature things, they emit most of their light out at wavelengths that are beyond what we can see with our eyes. And so they show up very nicely in these infrared surveys, even if they're invisible in the optical. So these technologies and these surveys really allowed us to discover the first brown dwarfs. And so these were starting to be found in the 1990s. This is just a sample of some of the first discoveries. One of the most popular, and we'll see this one first probably a few times during this quarter, Lisa 229b is a companion to a nearby M dwarf. That's the kind of big, huge, bright thing off to the side. And then there's a little faint thing next to it. Again, this was detected because this is an infrared image. Previous optical images could not see this companion to it. Here, these two things are just kind of random red objects that happen to be floating around. And it turns out both of those are young brown dwarfs. And one of the reasons we know that they're young is when we take a spectrum, we talked about optical spectra yesterday. So in the optical band, particularly around about 813 nanometers or so, there's another one over at 6,700 nanometers, 670 nanometers. There's a feature that comes from lithium, right? An absorption line from a lithium atom. And that's important because if we go back to our proton-proton chain, lithium is down here as one of the third parts of the chain. And this particular reaction where lithium combines with a proton to make helium, that's the last step of the chain, is a very fast one. What that means is that it happens at a lower temperature than sort of normal hydrogen fusion. This is the thing that requires the most temperature, very top reaction. This one can happen at lower temperatures, it can happen pretty quickly. And this actually destroys lithium inside stars. So within kind of the first 10 to 100 million years of the star's lifetime, it is actually fusing away most of lithium. And when we look at low mass stars that are fusing hydrogen, they often have no lithium at all in their atmosphere. All the lithium has kind of been pulled down into the core, destroyed, and not replenished. The stars are very good at getting rid of the universe's lithium. But at low enough temperature, this reaction won't happen. Because at the lower temperature than hydrogen fusion, if we see lithium in the atmosphere of particularly older stars, that's got to be a brown dwarf, because that lithium should have been destroyed by a nuclear reaction. So this is an example of one of the clues we use to figure out what's happening at the core of the star. Remember, when we differentiate between stars and brown dwarfs, we're talking about fusion, right? That's something that happens at the core. We can't watch that happen. Almost, right? There is a way we can watch fusion happen. We can do it with our sun by detecting neutrinos. Detecting neutrinos from this reaction. Right? We can detect those as they fly out from the inside of the sun. But we're not seeing any of the light that gets generated at the core. Right? But we can look for the products or the things that are destroyed by nuclear reactions. And lithium is one of these important ones. If we see lithium in the atmosphere of a star, either it's a very young star or it's not a star, it's a brown dwarf. So that's often called the lithium test, and you might see that in some literature. Okay? Questions on that? All right, so that's how we knew some of the first brown dwarfs were actually brown dwarfs. We know that they're everywhere. We find them as young cluster members. We find them as sources that are near the sun. We find them as objects that are clearly formed very early on in our galaxy because they have weird orbits in our galactic system. And very often we find them as companions to other stars. In fact, that's how we found the first one. We just looked for see if there's any faint things around nearby other faint things. And if they were fainter, that could be a cooler object that's a brown dwarf. Very tried and true methodology. And in fact, all of the prototypes for our new spectral classes, which we'll talk about in just a moment, are companions. So back in the 1980s, this object here is a white dwarf. This is the remnant core of a star that has fully depleted hydrogen blown off its atmosphere, and this is just the remaining core left over. And it had this kind of red smudge next to it. That red smudge was an object that was cooler than any M dwarf we had found up to that point. 2.9b, I just mentioned, is this object, and that is the first T-dwarf. That's a new spectral class. I'll show you why we know that in just a moment. And then we now have an even cooler object called Y-dwarf, and this one is another one that's found in phase of white dwarf. These are two images taken apart by 5 years. And you can see that both of them are kind of moving in the same way. That, remember, is proper motion. And often when we see two objects nearby that are moving with the same proper motion, that usually means that they're gravitationally bound to each other. So we know then the distance of this, use that distance to infer that this is a really, really low temperature object, about 300 Kelvin. About the temperature of the as a star. That's really extreme. Okay, so when I was a grad student, this is me as a grad student. I used to wear rollerblades all the time and really long hair. One of the things I did as a grad student is I worked on spectroscopy of some of these new discoveries. In fact, my thesis was the discovery of this new class of things called T-dwarf. And I did it, you can't really see them very well, but I did it by looking at the infrared spectra of these objects and organizing them into a sequence. And that sequence ultimately became known as T-dwarfs. And those are these objects down here. So this is now a set of 4 spectra. This is covering the optical, but also the infrared. Remember, the infrared is important for these 4 objects. This top line is a spectrum of an M dwarf that's got, looks like kind of like a black body-ish kind of thing. It's got some strong absorption here from the metal oxide we mentioned yesterday, and some other M elements. This is an L dwarf, and then this is a T dwarf. Notice that this spectrum is very different than the other two. That's why it's a different spectral class. And it's different because it has methane in its atmosphere. Like, now we have some methane in the atmosphere, not much, fortunately, because it's bad greenhouse gas. We have more methane now than we usually do, and that's not a great thing. But many of the solar planets, like Jupiter and Saturn, in fact, this is a spectrum of Jupiter, also have methane in their atmosphere. So this is an object that has molecules in its atmosphere that are very similar to molecules that we see in the giant planets of our solar system. Very different than a star. And again, that means that this must be a pretty cool low temperature atmosphere. It's about 900 Kelvin. Because otherwise methane would break apart. It would form carbon monoxide, which is here. But we use these different, just like I showed you yesterday, we use these different clues. How do different elements show up in the atmosphere or in the spectrum? How does the shape of the spectrum change? That tells us about the temperature. And it also turns out it will tell us about the surface gravity, which is really massive. But these are the 3 main classes that we'll probably be working with: M dwarf, L dwarf, and T dwarf. There's a Y dwarf class, but those are so faint we don't have a lot of good spectra for those, and they're not going to show up in the spec data so much. But these are new spectral classes that got added in the late 90s and 2000s because of our ability to detect these very cool dwarfs. The original spectral types were defined in 1940, so that's a big time span. This is more schematically about what these look like. So this is going down in temperature, right? So M dwarfs, again, these are the most common stars, but they can also be very young brown dwarfs that haven't had time to cool off. The L dwarfs are in this range of temperatures, 2100 to 1500 Kelvin, and they are interesting because they actually have clouds of dust in their atmospheres, and that has some implications about how they look over time. This is the class that I studied, these T dwarfs. They go down to 600 Kelvin, and they have atmospheres that have water, methane, and ammonia. All the elements are molecules that we often see in some of our giant planets. And then this is the newest class of brown dwarfs that go down to at least 250 Kelvin. And these have other cool things like salt clouds and sulfide clouds, and the coolest things might start to form water clouds that we have here on the Earth. That's pretty cool. But these are all sort of brown dwarfs because they're all much colder than the temperatures we can get for normal stars. Questions on that? Time. Yeah.
So for these like star classification systems or brown dwarf classification systems, is it like a timeline, like an M dwarf will turn into the next one? Or is it
Anticipated my next slide. Yeah, so if we put that range of temperatures remember I had this temperature versus time plot from the sort of theoretical model. If I put that range of temperatures on here, if you follow like one of these middle red lines, so like these lines that, this is like a 5% of mass of time. That object is an M dwarf when it's something like 100 million years old. It cools off into an L dwarf, maybe when it's 300 million years old or so. And then it cools off to become a T dwarf when it's like 2 billion years old. And if it keeps going, it'll eventually turn into a Y dwarf at about 10 billion years old. So yeah, this MLTY sequence turns out to be a sequence of evolution for these objects, which is different from stars. Remember, for stars, they stop at a certain temperature. So we see a stellar M dwarf. That temperature corresponds to one mass. If I see an L dwarf, it could be, this brown dwarf that's in the middle of cooling. It could be a really old star, right? If it takes long enough, if it's right near the hydrogen burning limit, it can cool off to be an L dwarf in enough time, and that would be a star. Or if it's really young, it could be one of these planetary objects. So this fact that these brown dwarfs change temperature over time and change spectral class also means that there's kind of a degeneracy here. If I know the spectral class of objects, it actually could be a very wide range of objects depending on its mass. So that's not something we see with stars. So by the way, the understanding that stars fuse really came out in kind of the 1930s. Before that, people thought that stars just shrunk and got colder over time. So the sun was literally in the middle of that evolution and would eventually become an M dwarf. And that's why you'll often see when you hear talks or astronomers talk about stars, they'll talk about early type and late type stars, because this is left over from pre-nuclear physics. People literally thought the only way you can get a star to produce energy is just to allow it to continue to collapse and cool off. Turns out the time scale for that doesn't work out, right? That would mean all of our stars are, 50 million years old and less, right? But we didn't know what fusion was doing, what fusion was 100 years ago. So we still have that language around. You'll hear people talk about massive stars as early type stars and low mass stars and late type stars, because that's left over from the time when we thought all stars just cool. We now know that those temperatures are based on the mass, and they stay at that temperature for a long time. But brown dwarfs do go from early type to late type over time. So we've kind of gone back to that, yeah.
So like the stars, when they stay at a constant temperature, do they have their own kind of timeline of evolution as they change?
Yeah, I mean, you kind of see it here at the bottom of the plot, right? So it takes some amount of time for them to get to the main sequence. So these very massive stars pretty quickly get to their equilibrium temperature. And then sometime much later on this chart, they will eventually run out of hydrogen in their cores and they will evolve off the sequence. And you get a whole bunch of range of different phases of that. You can see this star actually takes a long time to get to that balanced temperature. It takes a few billion years before it's kind of on the main sequence. So there is kind of a variation in time scale for that. And then there's a variation in how long they fuse hydrogen. Because the more massive the star is, the higher the temperature is core, the higher the pressure is core, so the faster it's running through its hydrogen. And that's why we're talking about that the massive stars in young galaxies die in a few million years, because they literally run out of hydrogen because they're burning it so quickly. Whereas these things are low luminosity, so they don't need a lot of energy from fusion. And so they take a long time to go through. So lifetime also depends on that. Brown dwarfs, on the other hand, don't run out of hydrogen because they never fuse it. But they do just get cooler and cooler. So brown dwarfs are going to be around forever. They're just all going to be really cold and can't touch them. So, it's a long-term investment. Other questions? Okay, I think I see a chat question. Okay, Luke asks, when we say these brown dwarfs are invisible, is that just from far away, that there's not enough visible light emitted to reach us, or is it completely invisible if we are super close? It's a good question, Luke. Certainly, if we were, say, in orbit around a brown dwarf, we would see it. It would be probably very, very red, because we're seeing just a little bit of the radiation that's coming from it. So there is, for example, we do study the optical spectra of brown dwarfs. but we often need to do it with a very large telescope because they are so faint in those visible bands. And I should say, even the coolest ones, the ones that are down here in the wide dwarf regime, 500 Kelvin ones, we often can't see them in the near infrared. We have to go out to the mid infrared to detect them, because again, that peak in their black body spectrum, lambda T of 2900 Kelvin, if we're down at 500 Kelvin, that's 5 microns, 6 microns where they peak. That's out in the mid infrared range. So as they get cooler and cooler, less and less of their light comes out invisible. So you could see them if you're right up against them, but even with the largest telescopes, we have a hard time studying some of the coolest examples of these. Okay. All right, I think that's a break. So let's take a short break here because I've been talking for an hour and a half. If you want to stretch your legs, there's a bathroom around the corner, and then we'll wrap up. We'll take maybe like a 5-minute break here, and then we'll wrap up in that last 20 minutes. Okay, welcome back, everyone. So I'm going to spend the last kind of 15, 20 minutes here to just do a little motivation about why we study brown dwarfs and kind of what's cool about them, literally. And, you know, again, for your research projects, we're not necessarily going to investigate all of these questions, but they always kind of form the background of kind of what are the sort of higher goals of some of the work we do. So when we're like focusing on like trying to understand like one little brown dwarf, you know, part of it's just understanding what are the big questions that are related to brown dwarfs and why we do these studies. So this is just kind of like some of the, I would say, the big areas of physics that we are interested in terms of these things, right? So there's like these general terms like the physics of stars, right? That's like, you know, how do we know the physical parameters? How do they evolve? How do they form? Right? There's all these kind of questions about just how they work, right? And one way to figure out how a star, which is fusing, works, is to understand these brown dwarfs, which don't fuse, right? What are the limits of star fusion mechanics? We can probe that, particularly at the limit between brown dwarfs and stellar systems. The atmospheres themselves, because they get down to low temperatures, become pretty complicated. We'll see a picture of Jupiter a little bit later on, but we just, you know, if you see Jupiter, by the way, did anyone see the lineup of planets this morning? Ah, nice. I couldn't see Mercury this morning, but I saw everything else. It was pretty cool. So it'll be around for a while. So I would get, this is like just before sunset. So you're an early riser, or if you stay up all night like me and we're observing, you can go outside and see it after. But, you know, so if you look at the atmosphere of their own giant planets, they're pretty complex. They've got clouds, they've got different colors. And now we've got this class of objects that span stars all the way down to those kind of planets. So there's a whole bunch of kind of atmospheric physics, chemistry, dynamics that comes out and just studies atmospheres at different temperatures. As we'll talk about, you know, these are pretty common objects, and so they end up being some of our nearest neighbors to the sun. And we're just finding them for the first time. And so there's still this kind of underlying question of how many brown dwarfs there are. There's definitely not enough to make dark matter. We'll talk about that in just a moment. But there's still some of our nearest neighbors to the sun. And so they're, you know, if you're really thinking kind of big scale speculative future, right, these may be places that someday, if we become a interstellar species, we might actually go and start visiting because they're so nearby. On the other side, if we're not there yet, we can still use them as places to study like how the sort of solar neighborhood sort of formed, what is the composition of it. And these are, of course, the nearest systems, so we can study them in the highest detail. So they're definitely targets of our new telescope. We'll see that some of these actually have planets orbiting them and potentially habitable worlds in some cases. We'll see examples of that in TRAPPIST-1. They are super dense, and so they actually could have some exotic states of matter in their interiors. These are actually, we'll see, the densest hydrogen objects in the universe. And we're only just now getting to the point where we can barely experimentally probe what the conditions are inside interiors. And so that's an interesting thing. We'll talk about dark matter a little bit, and then because these are a population of the Milky Way, and a very abundant population of the Milky Way, and every brown dwarf that's ever formed is still around because they never die. These are a potential way of just tracing the history of how the Milky Way formed, or different parts of it. And so in particular, for example, you know, Project Angelica that you're doing, you're looking at the oldest kind of populations in our Milky Way. So they're kind of snapshots of its early history. So brown dwarfs in those populations are interesting for us as well, but also just broadly in galaxies. So these are kind of the ways that I often think about brown dwarfs and their intersections with other science questions. So again, just thinking about the, sort of the fact that they're very peculiar. So this is just kind of some of the sort of key details of the physical properties of these objects from the atmosphere down to the core. Again, the temperatures have to be pretty low, particularly if they've cooled over time. And then their interiors are interesting because, first of all, they're very dense. And so the kind of type of material that you have here is what we call a strongly coupled, partially degenerate plasma. So partially degenerate is that electron degeneracy. Strongly coupled means that the particles are so close to each other, they actually interact with each other as plasma particles do. Their plasma is hot enough to be ionized. And in fact, it's so dense that in some cases we think that perhaps part of the regions inside these are actually hydrogen metals. Now, hydrogen is a gas, normally. If you get really, really cold, you can maybe make it liquid, but that's still not a metal, right? A metal is the kind of thing you talk about metals, iron and stuff like that. But at very high pressures, you can actually compress some materials down so they start acting like metals in the sense that they can conduct electrons very efficiently. And this has a consequence on how these objects can have magnetic fields, because it's really kind of in the sort of electrical currents inside planets that generate magnetic fields. So if you have a thing that conducts electricity as the composition of your interior, you can make a very efficient magnet. And we see some evidence of that today. Like most stars, they're mostly hydrogen. This is diffraction by mass. So yesterday we talked about by number, but because of course helium is 4 times more massive than hydrogen, by mass about 25% of the stars, although that will vary for different populations. And then they're convective. And we haven't talked too much about sort of stellar interior physics, but we're trying to get energy from point A to point B. There's only really a few ways to do it. We can either radiate energy, right? So we can use photons to send energy from here to here. We can, we have like a table, right? I can make this side of the table hot, and eventually that heat will conduct over to that side of the table. So that's convection. In a liquid, which is kind of like a plasma liquid, you can convect it, and this is literally conducting heat by just taking the hot stuff and moving it somewhere else. This is what happens when you boil water, right? When it gets to that kind of churny part of the boiling, that's convection. And that happens because it's just more efficient to just take the hot water that's near the burner and move it to the top, right? It's buoyant, so it's kind of close up. So that's convection. And these objects are fully convective from bottom to top. The inside of the sun is not like this. So the inside of the sun is, or I get this right, convective in the middle. Convective in the middle, it's convective in the middle, and at some point it's low density enough that light could actually conduct, so radiation can conduct heat in the outer layers. Really, really massive stars, I think, are the opposite. They're radiated in the middle, they're convective on the outside. These are convective top to bottom. So that means that anything that we see in the surface and the atmosphere that we can see with our telescopes has at some point passed through the core. And that's, for example, why lithium is totally gone in the entire star after a certain amount of time, because all lithium is destroyed down here. The lithium down here, up here, eventually makes its way down and also gets destroyed. So we have a very uniform composition object. And so anything we study up the atmosphere is actually pretty representative of the stuff that's happening out of the atmosphere. That's not common for most stars, but it is for low mass stars. And then, as I mentioned, the core is very dense, and so it can be up to 1,000 grams per cubic centimeter. 10 to 11 bar, which is probably a unit you're not too familiar with, but this is 1 bar is our atmosphere. So like in our room right here. So this is, almost 1 trillion times, 100 billion times more dense, or more higher pressure than that. This is in fact some of the highest pressures that we see in high-pressure objects. And again, these are relatively cool, relatively speaking, because they can't diffuse these hydrogens. So these kind of conditions make brown dwarfs literally the densest hydrogen objects that we know of. So this is a plot showing the average density in grams per cubic centimeter Jupiter masses. So Jupiter is somewhere in here, right? The sun is somewhere over here. And notice that as we go from something like the sun down to lower masses, the densities go up. And again, that's just reflecting the fact that we have to shrink stars down in order to start those fusion reactions. We're shrinking them down, the densities are going up. And then right here at the maximum of this is right at the 7% of the mass of the sun at Heisenberg. Literally objects right at that boundary are the densest of these hydrogen objects. And I keep saying that because we do have denser stars out in the universe. Things like white dwarfs, neutron stars, and of course, ultimately black holes. But those are actually made out of different elements. This is the densest hydrogen. Then it gets lessened because other forces start to come into place. Now, this is so dense that this is really kind of at the limit of what we're able to do experimentally. So this is a very different kind of study. This is, how many of you have heard of like the kind of fusion studies that are happening up at, I think up at Lawrence Livermore, where they're taking all these lasers and they're sort of aiming it at this tiny little target and causing it to implode and trying to make fusion happen. Have you guys heard of this laser ignition fusion before? Okay. So there's a couple of kind of main, so fusion is like, one of the things that people keep talking about is our energy source of the future, but it's always in the future. It's like every year, it's 10 years in the future. Because it's really hard to do, right? Stars do this really well, but they're doing it on the bottom of a star, right? We don't have that kind of mass around to do that. And so, we're trying, again, get things to be close enough together at high enough temperatures to then fuse and release a lot of energy. And so one of the ways they do this is they take like 128 lasers and they fire at one little capsule and cause it to implode. And hopefully at high enough speed that will actually start fusion for like a nanosecond. And then it blows up and we don't have anything. How many of you watched, by the way, the show, the space show? We just canceled it. The Expanse. Nice.
I know you're a fan.
Yes. So, is anyone a fan of Expanse? Because otherwise, this would be totally irrelevant. Okay, never mind. All right. They have laser fusion in Expanse. It's great. Anyway, so this is experiments from that kind of research where they're trying to test these kind of fusion reactions. So this is showing a bunch of different things all at once. This is showing models for Lisa 290. Remember, that's that first T dwarf that was found. And this is showing what the temperature as a function of radius looks like in times 10 to the 4. So for example, this is going to be 1,000,000 degrees Kelvin right here at the 4. Black line is the pressure in units of 10 to the 9 bars. So this line right here is 2 times 10 to the 11 bars. That's where that number came from. And then the blue line is the density in units of grams per cubic centimeter. And you can see we're going up to around 400 to 500 grams per cubic centimeter. Remember, the sun is 150. So this is really dense. So this is a model for the brown dwarf. And then these values are showing you kind of where these experiments are measuring. So right now we can get up to densities of like 50 grams per cubic centimeter, pressures of 100 grams or 100 gigabars. But the temperatures of these are actually up at like 6 million degrees Kelvin or more, right? Way off the spot. So we actually cannot, at this point, experimentally test what the matter looks like inside these brown dwarfs, because it's actually beyond our ability to make them, to set up material in that way. So the other way to think about it is that brown dwarfs provide our only way of understanding what happens when you have relatively cold but extremely dense hydrogen, and where you get these kind of different states of matter. I don't know if I have the plot for this. I don't have plot for this. Okay. So anyway, so there's this intersection between experimental physics and brown dwarfs, but brown dwarfs are still this very unique system, this very unique environment that we cannot actually test in the lab because it's such an extreme environment. It is very high pressure, high density, but cold relative to what fusion reactions do. So there's a lot of people interested in brown dwarfs just because they're interested in how matter works. I mentioned that brown dwarfs are everywhere. This is a nice animation that my former grad student, Jackie Faraday, put together. We're zooming out from our solar system in this visualization, and then pretty soon you're going to start to see our solar neighbors come into view, and they're going to start to get labeled. So anything that you see in red there, excuse me, are the known brown dwarfs in the solar neighborhood. And there's quite a few of them. Everything you see in blue there are systems that have planets in orbit around them. So, you know, we're really embedded in a large population of cool things, whether they are cool things that are floating around by themselves, the brown dwarfs, or cool things orbiting other stars. And there's a lot of connection between those two objects, because in some cases, the planets are giant planets that sometimes have exactly the same temperatures and properties as the brown dwarfs that are just floating around by themselves. All right. Now, I said they're very common, but they are not dark matter. So this is a kind of a fun plot of this. So right now, our best guess is that the number of brown dwarfs relative to stars in the Milky Way, at least in the solar neighborhood, is something like 20% or even up to 1-to-1, which is still amazing because remember, we found the first brown dwarf in 1995, it was about 30 years ago. And they represent possibly just as many objects in the Milky Way as all of the stars that we've been looking at for hundreds and thousands of years, right? So that's a pretty big population to just kind of stumble upon. However, if we're looking for dark matter, we need to have something like 20,000 brown dwarfs for every star. So we're not even close to that, right? If they're low mass, they need to be much more numerous in order to make up that dark matter. So they're not dark matter. No one's going to get a Nobel Prize for them, unfortunately, unless we find them as a companion to the sun or something like that. But they're still, as I said, our nearest neighbors. And so this is a recent kind of plot showing some of our nearest neighbors. Here's the sun here, and then this is going out in steps of light years. Here is the Alpha Centauri system. You can see this from the southern hemisphere. So there's no discovery date for that because we've been able to see it with a naked eye for a long time, although it has a companion called Proxima Centauri, which itself has a planet, actually 2 planets, that was first discovered back in 1917. So it's the first time that they saw that there was a third star around Alpha Centauri. There's another star that was discovered around the same time called Barnard's star. This is I actually showed an image of this yesterday, this very fast moving star. It's an M dwarf. And then just outside there, these 2 other systems that have little brown circles because they're brown dwarfs. These are 2 sets of systems that were found just in the last 10 years or so that were discovered because of these infrared sky searches. And they are, the next systems out compared to these nearest systems that we've known about for over 100 years. And yet these were found just 10 years ago. So they're really nearby systems. Now this one looks really nearby, right? But the interesting thing about this is that this is a system called Schultz's star. It's actually a pair of stars. It's an M dwarf and a T dwarf. And this is where it was about 70,000 years ago. We know this because we know its velocity vector very well. We can trace it back to where it was in time. And we know it had a pretty close pass by the sun about 70,000 years ago. Now, you might say, oh, maybe there are records of people seeing the star. It would still have been invisible to the naked eye, even though it could have passed close to the Earth. So these are really hard systems to study. In fact, as I mentioned, Proxima Centauri and Barnard's star, 2 of our closest stars, are invisible, and that's why it took until 1910 to discover them for the first time. So there's actually a lot, even near the sun, that we're still finding because they are so faint and so hard to see. And part of what we're doing in this research is looking for more of these kind of nearby things. We have like a couple news sources, for example, just in the last month that we found that are about 30 light years away. So it's kind of off the scale of the chart, but that's still relatively close compared to these most of the stars that we see in the sky. So they are nearby things, right? There's a sort of infographic about Schultz's star. So there it is passing through our solar system. The closest approach we think was roughly about 50,000 astronomical units. Remember, an astronomical unit is the distance between the sun and the Earth. So 50,000 is well past the orbit of the planet, but it is out in the region where we think a lot of our long period comets come from, a place called the Oort cloud. And so it's possible that they could have shooken up some of these rocks and they're coming in towards us today. It's going to take 2 million years for them to get to us, so there's no rush to panic at this point. But it does suggest that maybe these kind of close passages happen every once in a while. And they may, or maybe very likely happening from these very low mass stars, which we're just finding them for the first time. So that's pretty cool. One of those stars in this picture, 0855 at the up top, and by the way, these represent the coordinates of the star. Right? So this is a shorthand for the right ascension and the declination. So it's about 10 hours in right ascension and minus 53, which means that's down in the south. We can't see that so well. I have pointed Keck at the star, and it was not a pleasant experience, but we got some data. This star is a little bit more towards the equator, so we can see it, but it's extremely faint because it is only about, so again, about something like 250 Kelvin or minus 20 degrees Celsius. So the atmosphere of this star is colder than freezing water. Again, weird thing to think about for a star, but that's what happens with brown dwarfs. If they have a lot of time to cool off, they just get colder and colder. And the lower limit is just coming into thermal equilibrium with the universe, which is 3 Kelvin. So they have plenty to go down to lower temperatures. And again, this is only about 2 parsecs from the sun, which is really close. Something like the 4th or 5th closest star to the sun. Found back in 2014. Now, at those low temperatures, when I talk about brown dwarfs, I mentioned that they have stuff like methane and water and ammonia. So this is kind of a fun infographic of some of the other molecules that we see in some of these spectra. So things like titanium and vanadium oxide, metal oxide. We have metal hydride, like iron hydride. And then we have carbon dioxide and carbon monoxide that are present in these atmospheres. Both of those molecules have been detected. Again, all of these are very familiar because we also see them in planetary atmospheres like our own atmosphere. Now, these are all gases in the atmospheres of these objects, and we can see them because of their absorption features. We're also in the regime where things can melt or freeze depending which way you're going, right? So if we take some of the, some substances like water, so water, freezes out at 100 degrees Celsius. So, sorry, that is not right. It should be 0 degrees Celsius. I think it vaporizes. Vaporization, so it vaporizes 100 degrees Celsius. So if you go below 100 degrees Celsius, you can have liquid water. Totally fine in our atmosphere. Our atmosphere is less than 100 degrees Celsius, so we have liquid water clouds. But there are other substances that vaporize at much higher temperature. So things like rocks vaporize at like 1800 degrees Celsius or so. Metals are really hard to melt. That's why when we want to make something out of iron, you have to develop a technology that can get to temperatures that are way higher than what we normally get in like a fireplace or something like that. That's why we have these massive factories that work with these metals. But these temperatures, at least on this side, are of the approximate order of the temperatures of the atmospheres of some of the brown dwarfs we study. So again, if we think instead of taking something and melting it by increasing its temperature, we could go the other way. We can start with a really high temperature atmosphere and cool it off. And what's going to happen is that this stuff is going to start to condense out of the atmosphere. So there's a lot of, in addition to the gases, there's also condensates and stuff like that that also form this atmosphere. And they're literally rocks and metals, right? These are clouds of very hot rocks and metals, right? So, imagine having weather that's made out of molten iron. It's not pleasant, right? But it does form a different kind of substance in the atmosphere than we normally have in stars, but we do have in planets, right? Clouds of condensates. And so there's a lot of studies to understand, and by the way, some of those are also gems. So corundum, which is one of the things that condenses out, if it has impurities, makes all of these different kinds of gems. So, this could be a good mining operation if you want to go find gems in brown dwarfs. But we think that there's a whole bunch of these things that condense out. And so this is going from higher temperatures to lower temperatures, and then high up in the atmosphere and lower in the atmosphere. And you can see that, for example, in these L dwarfs, we get these rock clouds. We also get metal clouds in their atmospheres. This is not something, by the way, we have in any planet that we've ever looked at directly, right? Our planet, fortunately, is not hot enough to have molten iron clouds. Jupiter and Saturn, those clouds are probably there, but they're super deep in the atmosphere, so we don't see them. So these are the only objects that we know about that have rock clouds. And so that's kind of, if you're into atmospheric chemistry or atmospheric meteorology, this is pretty neat because it's a completely different kind of system than we normally have. Now notice that as we go to cooler objects, these clouds just settle down deeper in the atmosphere because, of course, you know, the average temperature is here. As we go down, it gets hotter. So we've already get to the same temperature, we have to go deeper in the atmosphere. Above these, then other clouds can start to form, other substances can start to mix up. So in T-dwarfs, the things that I studied as a grad student, we also think that there are things like sulfur clouds, possibly some salt clouds, right? Cesium chloride, rubidium chloride, potassium chloride. Potassium chloride is like a salt you can find in the Salton Sea. This may just be floating around in the atmosphere of these red dwarfs as well. And then we get to cold enough temperatures, you start to get the clouds that we're more familiar with because you're getting into the same temperatures as our atmosphere. So we think at some point, and perhaps we have already detected it, that we might start to see water clouds, which is the clouds we have here on Earth, or ammonium clouds, or even ammonia clouds, which we have in Jupiter. So from something that's very exotic and very different to perhaps something that's a little bit more familiar to what we have in our own solar system. Again, from a meteorologist or atmospheric scientist perspective, this is a super rich area because there's a lot of chemistry here that we just don't see in the bodies that we've studied so far. Now, the other thing to keep in mind is that when we look at clouds in our atmosphere or in other planets like Jupiter, right, they aren't just, like, it's not like the spherical cow, right? They're not just like one cloud that covers everything, right? They have structures to them. Right? We have patchy clouds, fog, mist, storm clouds here on Earth. On Jupiter, you have these bands of clouds that are at different layers, different heights, that move in different directions, that form storms like the Great Red Spot. So there's a lot of dynamics that we can see that are traced by these clouds. Unfortunately, when we study brown dwarfs, we only just see these dots, right? So we can't see these kind of structures because they're too far away. One thing that you can do is, for example, if you just watch Jupiter over time, if I were to kind of integrate all the light in here, particularly as the Great Red Spot comes by, you would see that the light that we see actually changes over time. Right? The red spot is darker than the rest of this, so as it comes in, it actually causes Jupiter to get a little dimmer. And then as it rotates around, we just see this kind of coming back in and out. So we can use the fact that we know that as planets that have structure on the atmospheres change brightness as they rotate, we can use the same effect for brown dwarfs. And so this is a study I helped out with a few years ago, where we observed a brown dwarf that did this. So we were observing it with HST, and it had this kind of weird light curve where it suddenly started to change. It got changed really big and got even bigger. And we can model that behavior by making a model for the brown dwarf that's actually not too dissimilar to what the planet Neptune looks like. Neptune has these bands around it that have spots. These bands travel at different rates. And so what you see in front of you will change in complicated ways. And so we made a very simplified version of that, right? Just kind of stripes instead of these complicated bands. And we're able to make a model that actually reproduces this behavior pretty similar. So we're literally starting to make models of what the surfaces of these brown dwarfs look like because of these clouds, even if we can't see the clouds directly. So that's a lot of detail that, again, we won't normally get with stars, but we can because of the clouds on brown dwarfs. Here's another study that actually used high resolution spectra to map dark and bright structures as they came into view on the brown dwarf. So you have actually like the world map for brown dwarf, even though we can't directly resolve the surface itself. So not only is this kind of cool, you're mapping stars, but this is also really important for understanding the dynamics of these objects, right? Because these clouds, the sizes of the clouds, where they reside as a function of latitude, how they rotate across the surface is all related to the internal dynamics of the atmosphere itself. And also that's related to how energy gets out of the ground. So there's a lot of detailed physics, and there's a lot of folks who are building complicated models to try to reproduce these kinds of observations. But again, this is all because we're in this regime where stuff can condense out of the atmosphere and make stuff. It's not something we can. Okay, any questions on that? Those of you working with spec data, like you'll probably be working on things that are in the kind of L dwarf regime, and all of those systems, as far as we know, have some kind of cloud dot. So You'll be seeing this a little bit in the spectra as well. All right, this is just another comparison to show that, you know, when we look at the atmospheres of brown dwarfs like this T dwarf, they look a lot like planetary atmospheres. Right? So this is Saturn. This is taken, both of these are taken with a spectrograph. This is on a particularly cloudy night, because otherwise these saturates the instrument really quickly. You can see that the structures are very similar because they have the same kind of absorption gases in their atmospheres. Now, the equivalents of these are actually difficult because one of the things that, you know, we're still struggling with is, where do we draw the line, right? They look a lot like giant planets. It's possible they form a lot like giant planets. And we also see brown dwarfs just floating around that have the same masses as some of the giant planets that we're finding in other studies. So this is a few years ago, we had a conference out in Spain, and we had people vote on different objects to say, you know, like this thing, is this a planet? Is this a brown dwarf? Is this a planet, or is this something else? And these are all experts been working on the field for decades, and they couldn't come to agreement on what these things are. So the existence of brown dwarfs is actually kind of challenging our understanding of what these astronomical objects are. Before 1994, it was very easy to say what a planet was and what a star was, right? There was nothing in between, right? The biggest planets we had were Jupiter. The only planets we knew about were in our solar system. And then stars were totally different objects. Brown dwarfs are somewhere in the middle. And they're starting to kind of like challenge how we actually categorize these things, because it's not clear if they form differently or similarly, and if they have different properties that we can actually tell. The last point I'll make is that, you know, brown dwarfs themselves can also be the host of planetary systems. And probably the most famous of these is the TRAPPIST-1 system. How many of you have heard of TRAPPIST-1 before? Yeah, if you're UCC, you have it. So this is it's not quite a brown dwarf. This is 8% of the sun's mass, so it's almost a brown dwarf. This is a discovery that I was a part of, where we were looking for planets around the lowest mass stars and brown dwarfs, and we found this really amazing system. Now we don't see this, right? This is all artist rendition, but this system has 7 planets around it, and we found it with this very tiny telescope down in southern hemisphere in the Sea Observatory in Chile. And what we basically did is we just stared at this star for a long period of time. And what we're looking for is something passing in front of the star. So this is called the transit method. And this is one of the most common ways that we find planets around other stars today. We're just lucky enough that the planetary system is aligned with our site of view. And as the planet orbits around, it just passes right in front of the star and blocks a little bit of the light. It's just showing where this brown dwarf is. It's very remote. So that's what these data look like. So this is just staring at the star. We notice that the light dips for a little bit and then comes back up. Does that for something like 10 or 15 minutes. And it happens periodically, repeatedly. So it's clearly something that's in orbit, so it's coming back again and again. So back in 2016, we found that there was one of these things that was coming back and again every day and a half. And then another one that was coming every 2.5 days. And then there was like one more that we just didn't know. We only had like one detection of it. We didn't know what it was. So we got a whole bunch of telescopes together and we stared at it. And this is data that we produced from the Spitzer Space Telescope. And this is a model of the planetary system above. So every time a planet passes in front, it dips the light down of the star just a little bit. So this is about 21 days of data with an infrared space telescope called Spitzer, which has been decommissioned. And you can see over that time, we get all of these little dips. Sometimes we even get little bursts. So you'll see one coming up here, right? That upward burst is a flare. Every time a planet passes in front, we get these little dips, and we can kind of see the periodicity of all these things and figure out, first of all, how many planets are in the system. And again, it was about 7. And also how far away they are from the star based on the periods in which they come back and forth. And let's see, is that one? Yeah. So this is the map of the TRAPPIST-1 system. This actually, if we put it in our solar system, fits way within the orbit of Mercury. Mercury takes about 88 days to go around, and these take from 1.5 to 20 days to go around the Earth. So these are really close in time. But because the star itself is such a cool star, it turns out that, depending on how you count, 3 or 4 of these planets are at the right distance from the star, that if they have atmospheres and if they have water on their surfaces, that water would be liquid. And that definition is formally known as the habitable zone. And these are the kind of planets that people are most excited about to find, because these are the sites that we want to look for potentially, living organisms, because all life on Earth requires water. We only know about life on Earth, so a good starting point is to look for things that need liquid water. To do that, you need to find places that have liquid water. And so this one system itself contains 3 planets that potentially fit that bill, although we don't know that until we actually get measurements of the atmosphere and potentially the surface, which might take another few days. But just finding these planets is exciting because it means that these are potential sites for looking for life beyond Earth. Okay, let's get that. All right, so that's it. Any questions about brown dwarf?